Welcome. Thank you for joining us this afternoon for the second in our SWAS webinar series. My name is Bob Abramson. I'm the head of marketing at Waltron, and we're looking forward to giving you this presentation, having a little Q&A on some of the instrumentation challenges with using form filming products. A little bit of housekeeping before we get going. Everybody is on mute, so we ask that you stay on mute just to keep background noise to a minimum. We will be doing a Q&A once we get through the presentation, so if you could submit any questions in the chat box in the bottom of the screen, that would be great, and we'll go through that Q&A. Yes, we will be recording this and sending out a link to the recording as well as the copy of the slides. You'll have that no later than a week from today, if not a little bit earlier. Let me just introduce the speaker for today and we'll get going. Again, we have Lucas Staub who will be presenting this to us today. We are lucky at Waltron. Lucas joined us, six months ago, and he is our Chief Commercial Officer. He is an engineer by training, but he's had a 20-plus year career in water chemistry. So he's someone who really knows his stuff, has seen things in action, and it's great to share some of his expertise with us today. So without further ado, I'm going to turn it over to Lucas.
Thank you for the introduction, Bob, and welcome everybody to this little webinar. As Bob said, it's going to be a deck of slides, probably about 25 minutes, and then we leave plenty of time for questions on instrumentation challenges in water steam cycles that are applying film forming products, film forming amines. Give you a quick overview on what we're going to talk about today. First, why are we applying film formers in water steam cycles? And I just want to mention this is not a presentation of different film forming amines, film forming products. This is looking at the consequences of the applications. We have to look at what are the different FFAs and FFP classes that you find in the literature, and then what are the effects of FFPs, how do they work in general. And again, I'm not going to go into the deep chemistry of the different products. The vendors of those need to do that. And then what we're actually looking at is the unintended corrosive consequences. It had this undertitle in the advertisement of the webinar, the unintended corrosive consequences of film forming products. And again, the chemical mechanisms and what the corrosive consequences if FFPs, FFAs are applied overdosed or not applied in the right way, then we're not going to go into too much detail. Where we're going to dive in a little deeper is the unintended effects on the analytical equipment. This is an interesting field, and we as an instrument manufacturer have done some studies that are, of course, showing some effects on instrumentation, and these effects are actually good to know. And we're also going to talk a little bit about mitigation strategies. And again, this is focused on how do I make my equipment run reliably rather than the unintended corrosive consequences, how to mitigate that. That's other experts' field to deal with. Now, why do we apply film forming products in water steam cycles? There is a couple of commonly known reasons for that. Asset protection, preservation of layups. Film forming products establish a barrier that remains intact during operation, but also in offline periods of plants, and this provides an excellent protection during operation, but also when you're looking at wet and dry layups without the need for extended nitrogen blanketing or dehumidification of the whole installation. Sometimes people also talk about safety and environmental benefits. This is mostly related to plants that are applying oxygen scavengers, as some of these FFPs and the mixtures of products that are applied then are said to be less toxic and more environmentally friendly than, for example, hydrazine when that is in use as an oxygen scavenger. Improved efficiency is another topic that some people like to talk about. By keeping heat transfer surfaces clean with the application of an FFP or an FFA, and promoting actually a drop-wise condensation rather than a film-wise condensation, for example, in condensers, that could actually significantly improve the efficiency or the heat transfer. And another topic that people mention when applying FFAs a lot is operational flexibility. As power grids shift towards flexible generation to support renewable energy, plants experience more frequent startups and shutdowns, peak shaving operations. Traditional treatments like ADT or also phosphate treatments in boilers, they have limitations in protecting assets when you're looking at the cycling operation of these plants. And so the application of FFA can, in certain circumstances, actually support the mitigation of corrosion formation in those plants. What are the different FFA classes? We generally find three different classes in the literature. The literature talks about film-forming amines. These are defined chemical substances, typically carbon chains of 10 to 18 atoms, commonly used, these ODA, OLA, OLDA, as mentioned here. And the second class is film-forming amine products. They're called in the literature FFAP. These are commonly blended products that contain an active film-forming amine, an FFA essentially. And then they are combined with other components like alkalizing or neutralizing amines, emulsifiers, reducing agents, and so on. So again, details on that is a topic for the suppliers of these substances. And then the last class that can be found in the literature is the film-forming products, the FFP. These are products that have the same film-forming properties, but then they are not amine-based. They often belong to a surfactant family, may contain carboxylate groups, and so on. So there is, at the end of this presentation, there is 2 pages with references of documents that can help actually getting you a little bit of an overview of what kind of products are available and what classes of products are applied in various situations of operational plants and what kind of plants you're looking at. Now, what are the different effects of FFPs? There are mainly 3 effects that we're looking at here. One of it is the formation of a hydrophobic barrier. With the molecular structure of a hydrophilic head and a hydrophobic tail that repels water, the other end is going to stick to the metal or the metal oxide surface and building that hydrophobic barrier. The physical shielding is the second effect that we can see. The molecular layer acts as a physical barrier, also preventing species like oxygen, for example, from contacting the metal surface, and with that preventing further corrosion. So in general, it can be said, actually, both of these mentioned effects, what we're intending to do here is corrosion mitigation. So the FFPs intend to reduce general corrosion, mitigate flow accelerated corrosion in both single and two-phase environments. It's like what we can find in air-cooled condensers and heat recovery steam generation. So now, just really quick an overview of the unintended corrosive consequences if those FFAs are applied in the wrong way, in the wrong application, in the wrong plant, in the wrong dose maybe as well. One of the most important one is the thermal degradation into organic acids. So FFAs and blended alkalizing amines undergo thermolysis, so they break down into carbon dioxide, which is not harmful, but then also in lower molecular weight organic acids. And that can trigger severe FAC if not treated in the right way. Another phenomenon that is reported and studied quite extensively, and again, I'm going to refer to the documentations that I have listed on the last 2 pages of this presentation. There is a lot of science behind the under-deposit corrosion as well. So you can imagine this layer of FFA being on a metal surface. If you have, for example, a thick porous oxide layer beneath that without prior chemical cleaning, that can lead to severe under-deposit corrosion when this layer of FFA or an FFP actually just is going to be stuck over an already corroded surface. Also, an effect that can be frequently seen, mostly in conjunction with dosing issues, the system plugging and gunk balls, especially in sampling lines. You will find that the deposits, the excess chemical can form sticky gunk balls that restrict flow or can actually clog tubes completely, mostly in the low pressure part of the plant. And last but not least, there is also mixed metallurgy vulnerabilities that I'd like to mention. Blended FFPs contain ammonia, and it can cause ammonia grooving into copper alloys, for example, while aluminum components, if they are in the plant, can suffer corrosion if pH is driven above 8.5, for example. So it has to be carefully examined what kind of plant, what kind of components are we looking at before applying these kind of film forming products. And now we're going to come to the unintended effects that such an application might have in terms of instrumentation, what kind of mitigation strategy we can look at. And this is where we're going to deep dive a little bit into different effects that you can see when applying FFAs, FFPs in general. And I'm also going to run through a couple of tests that we have done back at our lab. Our head chemist twin was actually conducting most of these research, basically. And I'm going to start with sodium analyzers. Sodium analyzers are essential for monitoring of water chemistry and especially detecting any upset condition under operation conditional. So what we saw as an effect was some kind of a sodium analyzer blinding when applying certain FFAs. Now, here's a quick rundown of the test procedures. The test was to recreate the result at a lower spike level for FFAPs, that can affect the accuracy and the response time, especially of sodium analyzers. So I'm going to actually run through this real quick and going to show you the test setup. So the methodology of the test, you can see this is the test setup. So two precise metering pumps are supplying DI water and then the concentrate of that sodium standard and the FFA standard, in this particular case, using a 50 ppb sodium mixed with a 45 ppb of a certain FFA. Actually, there was multiple FFAs that were tested. This here is the analyzer that was used for the test, and later tests also used in the very same setup then dissolved oxygen analyzers, both Clark cells and LDOs, and then pH and conductivity sensors where we looked at the effects that this might have. And later also we studied effects of filtration and how we can mitigate the effects that the FFA basically has on the analyzer itself. So what was the initial finding? The initial finding actually of those tests that were made was an upward drift in concentration. There was one of the products that was tested actually showed a significant accumulation of microbubbles on both the electrode and the reference electrode. And that persisted even after manual removal of the bubbles. That drift was actually very persistent. And it was observed that this deviation was not solely due to the presence of the bubbles, actually. Again, once we removed the bubbles, this upward trend actually continued, but it was some kind of an electrochemical fouling of the electrode surfaces. And this is, again, interference absorbed from film-forming products. What the test results were when we spiked was a sodium solution that was introduced by a grab sample for only like 15 minutes. So basically what we did was injecting a sodium spike, which would simulate an upset condition, a sodium ingress in a condenser leak case, for example. And we can see that there is a downward trend value observed for the subsequent result. And this might now lead to a false reading. So you might not be able, after the application of a film forming product of 3, 4, 5 days, we might actually not be able to detect such an upset condition. So we won't see the breakthrough. Though it has to be said, 50 ppb is not a gigantic spike, so you would still see a breakthrough of a higher concentration sodium solution, but still we need to find a solution for this downward trend, and maybe a cleaning or a filtration will be the solution. I'm going to talk about this a little bit later in the presentation. In general, there is a critical loss of sensitivity, a severe loss of sensitivity actually, because the FFA tends to stick to surfaces. This is the job that it needs to do when it's applied to a metal surface, and it has that tendency as well within electrodes, of course. Reference electrode drift has, again, this is more to a electrode fouling actually, rather than a real drift or clogging or a coating of the electrode. And that creates what I was just talking about, that false sense of security. You will not be able to see spiked sodium introduction through an upset condition. I'm going to continue with probe coating on pH and ORP and conductivity sensors. Again, the same effects are going to be seen. So when you apply an FFA, it's logical. This is supposed to cover a metal surface. A standard conductivity sensor is nothing else but a metal surface. And when you have a buildup of a film, conductivity values can actually be seen to be affected with a prolonged exposure of the FFA concentration. The good news is that the sensors are cleanable very easily, so there's just a little bit more maintenance maybe required if you're applying an FFA to make sure that your probes are running. On the pH, we did not see actually a big effect on the reflex pH combination sensor. Other pH glass electrodes showed very similar fouling than what we've observed on the sodium electrodes, basically. So there are obviously pH probe systems, reference systems, that are a little less prone to be affected by FFA application. Now, coating of dissolved oxygen sensors. This is a very interesting one, and I'm going to show you a curve that was done first with a Clark sensor, a standard membrane covered Clark cell. And it has to be mentioned that different membrane types, different membrane materials do react differently to the application of a film-forming amine. The example that you can see here has quite a dramatic drop in oxygen concentration. This is mainly clogging the membrane, and this effect has not been seen on a luminescent sensor, in example, because it doesn't contain a membrane. Technically, it does contain a membrane, of course, but because it's not a diffusion membrane where oxygen needs to pass through in order to create a measurable signal at the measuring electrode, it doesn't have an effect on the reaction of the sensor. So no fouling can be seen at luminescence technology here. Last but not least, I'm going to talk a little bit about elevated cation conductivity. And elevated cation conductivity, or after cation exchange, that's how that's the terminology that's used in the IAPS papers, for example, in the IAPS guidelines. Of course, when I was talking about this decomposition process that you sometimes see in the application of film-forming amines, and when that happens, there is also carbon dioxide being formed. Carbon dioxide is not a harmful contamination of your water steam cycle, but still it will actually show on the conductivity after cation exchange. Now, there is a pretty simple solution to that. You will probably just switch from a standard conductivity measurement after cation exchange to a degassed version, and you can eliminate mostly the effects of that. What will still be seen on the degassed cation conductivity is actually the effects that are coming from these organic acids that are also decomposition byproducts of this film-forming amines. So you will actually see those represented in the degassed cation conductivity, and that is a good thing to have because you want to be warned about these decomposition product. So here the cation conductivity will actually give you a pretty good indication if there is decomposition products in the water steam cycle. Last but not least, I want to talk a little bit about grab sampling and absorption of the film forming agent when you're doing grab sampling, and especially when you're doing grab sampling for the residual FFA that you're using. As always, the FFAs, FFPs, they have a tendency to stick to surfaces, and so they do stick to surfaces of like sample probes, sample tubes that are leading up to the sampling system, the SWAS panel, and they tend also to stick to all kind of glass bottles and containers that you commonly use for your grab sampling. So there is a certain protocol that needs to be established to make sure that your grab samples are actually going to be represented at the end of the day. So let's talk a little bit about mitigation strategies. So all we want to have at the end of the day is we want to have a reliable chemistry monitoring and control. And so there is a few steps that can help in establish good monitoring and good practice in monitoring. I'm going to start with continuous monitoring of an FFA. So there is various methods. Actually, there is, to be exact, there is two analytical methods to detect low concentrations of film forming amines. Now, generally, there is no approved method available for any other FFPs or proprietary mixtures of FFAPs, although some chemical suppliers, they do offer proprietary measuring equipment specific to their product. But it's not when you have a standard measurement application or a standard measuring method for sodium or anything else. The FFAs, the classes that I mentioned at the very beginning, ODA, OLDA, OLA, these can all be detected with either the Bengal rose or the methyl orange method. And there is online monitoring available. So continuous FFA monitoring then applied continuously is certainly recommendable. Then what I mentioned before, the degassed conductivity after cation exchange or the degassed cation conductivity monitoring differentiate between organic acid breakdown from the treatment and actual harmful impurities. So the continuous decase monitoring is highly recommended to have a very clear view on what is contaminants and what are unharmful substances that are byproducts of the film forming amine dosing. Now, dissolved oxygen monitoring, of course, you want to make sure that you don't have a oxygen sensor that has a membrane that is prone to clogging, because this will give you a false low reading of oxygen content. Again, the LDO dissolved oxygen measurement has been proven to be pretty fail-safe in all kind of environments of application of FFAs. And last but not least, to avoid sodium blinding, sodium analyzer maintenance and filtration, to some extent, operators must implement significantly shorter maintenance interval and calibration cycles to prevent blinded sensors or missing a critical breakthrough. Enhanced cleaning, there is some instrumentation that does automatic cleaning using a combined mechanical and chemical approach. So there is various procedure that can be implemented to make sure that your sodium analyzer is actually reading appropriately and is reacting in a meaningful time, so that's not slowed down in the measuring process. And then this is more a general recommendation, actually, the corrosion product monitoring. I'm going to refer again to the last two slides where there is a long list of literature that talks about how to do proper corrosion product monitoring. There is an IAPS guideline on this. And just so I have mentioned it as well, IAPS is actually running a series of webinars that have topics like corrosion product monitoring, where you learn how this is done properly and what the benefit of that is in the plant. This is not related strictly to instrumentation, but it is just something that goes along with the sampling system, and it's usually integrated into the SWAS panel that you have a proper corrosion product monitoring. And the robust grab sampling protocols, that's one of the things that I just mentioned before. So when you are actually doing grab sampling, make sure that sample lines are thoroughly flushed and samples should be captured in a PTFE or a Teflon or silicone-coated container, which has less adherence of the FFAs, so therefore not biasing the grab sample. Adding acetic acid to the sample container will adjust the pH and stabilize the FFA concentration. So if you want to actually grab sample for the FFA concentration, that is a procedure that has been also described in some of the guidelines of FFA application of IAPS. EPRI has a similar guideline for that, preventing molecules from absorbing to the walls prior to the analysis. That's like the goal of that grab sampling protocol. All right, so that's pretty much it for our presentation. Again, here are the two slides with a lot of references and useful guidance documents. I think the IAPS TGD is probably the most complete one that I could recommend to go through. They're all free documents, actually can be downloaded from their webpage. There is the TGD guideline with the TGD 716 that has a lot of useful information. And there is also the technical guidance document on the application of film-forming amines in fossil, combined cycle, and biomass power plants, the TGD 816. So this is also a very complete guidance document that has a lot of very useful information that should be consulted before jumping into application of film-forming amines in your power plant. All right. So excellent. Pretty much done with the presentation part. We got plenty of time for questions, answers, as far as I can actually answer your questions. I put the contact information out here of the Voltron group as well as for my personal email address and phone number. So feel free to contact me by email or give me a call if you want to further discuss any of the findings of the results that we have done in the studies of the impact on the instrumentation mainly. I'm happy to give you an answer if I have one, and otherwise I might know somebody who does.
All right, that's great. So if you have any questions, and I'll put them in the chat. And my interface, my computer, it's in the lower right-hand corner. It's the third icon from the left. It looks like a little note. Let's see, I got one here. This here. What are the different measuring principles available to detect film forming products? You mentioned a couple, I think.
I mentioned it, yes. So there is commonly they're both photometric or colorimetric measuring methods. So there is just two different chemical complexes that are generally used. One is the Bengal rose, that's the one that the Voltron analyzer is using. And then there is the methyl orange, which is actually an automated lab. It's a fairly complicated process. It has different detection limits, though, than the Bengal rose. But these are the two methods that are commonly used in instrumentation.
Okay, let's see. One more coming in. Let's see, what is the filtration porosity recommend? I'm gonna try. Easy for me to say. One more time. What is the filtration porosity recommended to avoid FFA fouling of sodium analyzers? What is the cleaning procedure for the probes?
Okay, so it's twofold question. Now, the filtration is a tricky one because we're not talking about a very fine mesh filter or anything like that, or a sinter filter or something like that. We're talking about a surface filter where you have, it's almost like a ion exchange. When you do cation exchange before the conductivity measurement, it's the same principle. Instead of a resin, you have beads of a plastic material in there that absorb the FFA so that it doesn't go through to the analyzer. And now I'm pretty certain the second question is going to be, what material is that? And that's one of the points that is still under investigation. We're trying to find the proper material to actually have the best absorption. So there is a couple of filtration materials that are under investigation, and I'm sure come 6 months later from here, we be able to actually give you pretty good results on what filter material to use. And then the second question was the cleaning method. Now, the cleaning method and what kind of chemical solution to be used to clean the FFAs off the electrodes is largely depending on what kind of AVs or film forming products that are applied. Again, acetic acid has been, in general, chemical that has been used for that cleaning. There is others also available in the market, but this, again, is more actually depending on the film forming AV that is applied.
Okay, excellent. Coming in, what is the major reason plant would go away from a traditional AVT toward applying FFAs?
This is a question that exceeds my comfort zone pretty much, because we've just been part of the Bristol conference of IAPS, where application of film forming substances are frequently actually a topic at the power cycle chemistry work group. And why you would want to apply a film forming amine, that really has to be discussed with chemistry experts, with consultants out of the industry that can link that application of a film forming product much more to the operation circumstances of the plant and then the metallurgy of the plant itself. So that why you would switch to that's beyond our expertise.
Good. Okay. Another one just came in. Abra, thanks you for the presentation. Asks, I was wondering what are the different products you used in your tests of impacts on instruments? Did you focus only on the 3 FFAs that you mentioned, or did you also try any FFPs?
We did try FFPs as well. I cannot disclose what they were because that's kind of like a non-disclosure agreement that we have with the suppliers of those FFAPs, for that matter, too. And we are actually continuing to do trials. So whenever chemical suppliers are coming to us and wanting to know if their product has an effect on any of the measurements that are commonly used in water steam cycle, we're continuing that research and work with these chemical suppliers. But we've tried quite a number of film forming products actually in the market.
Okay, great. All right, let's see any more. We'll give it another 30 seconds to see if anybody else has any more questions. So just to remind you, we'll be following up next week. You'll get a link to the presentation. We'll give you a copy of the slides. So you'll have all those references that Lucas quickly showed you. You'll have those at your fingertips. If you want to go online and drill into any of those, you'll have them. I am not seeing any more questions pop up. So I guess we can call this a wrap. I just thank you all for taking the time out and joining us. Thank you, Lucas, for another fantastic presentation. I always learn a lot. And thank everybody. Have a great rest of the week. And it's almost the weekend, so enjoy the weekend. And if you're under a heat dome, hopefully things will cool off soon. Thank you all.
Thank you very much, Bob. See you, everybody.